Welcome to Two Projects. In this video, we are going to explain the project Heritage Monuments Detection using Deep Learning. Introduction. Heritage monuments are invaluable cultural treasures representing the rich history and heritage of civilizations across the globe. However, their preservation and protection pose significant challenges due to factors such as natural wear, environmental degradation, and human intervention. Preserving heritage monuments is crucial for maintaining a connection to our past, fostering cultural identity, and promoting tourism and education. Yet, identifying and monitoring these monuments efficiently can be labor intensive and time consuming, especially over vast geographical areas. So, deep learning offers a promising solution by leveraging advanced algorithms to automate the detection and monitoring of heritage monuments. Deep learning techniques such as convolutional neural networks excel in image recognition tasks, making them well suited for identifying monuments from various sources such as satellite imagery, aerial photography, and digital archives. By harnessing deep learning, we can streamline the process of heritage preservation, enabling timely interventions and conservation efforts. So, governments, heritage conservation organizations, historians, and researchers stand to benefit from accurate and efficient methods for detecting and monitoring heritage monuments. Additionally, local communities and tourists benefit from increased awareness and access to these historical landmarks. Objective of the project. So, as I mentioned earlier, the primary objective of the project is to develop and compare multiple deep learning models, including VGG16, MobileNet, MobileNet V2, ResNet 50, Inception V3, Exception, TenseNet 169, ResNet 101, LeNet, EfficientNet V2S, and CNN for the purpose of detecting heritage monuments from various sources such as satellite imagery, aerial photography, and digital archives. And another objective is to assess the performance of these models using key metrics such as accuracy, precision, recall, and F1 score. By thoroughly evaluating each model's performance across these metrics, we aim to identify the most effective model for heritage monument detection. Ultimately, the project aims to contribute to the optimization of heritage monument detection processes, enabling more efficient and accurate preservation efforts. By selecting and deploying the best performing deep learning model, the project seeks to enhance heritage conservation initiatives benefiting governments, conservation organizations, historians, and local communities alike. Requirements needed to execute this project are software requirements. Software needed is Anaconda. Primary language used is Python. Front-end framework used is Flask. Backend framework used is Jupyter Notebook. Database used is SQLite 3, and front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Now we'll discuss the working modules of Law of Work. So the first step is importing required packages. In this step, we import essential Python packages such as NumPy, Pandas, and TensorFlow Keras. NumPy and Pandas are widely used for data manipulation and analysis, while TensorFlow Keras provides a high-level neural networks API for building and training deep learning models. These packages are necessary for handling data and implementing deep learning algorithms effectively. The second step is importing the dataset. So, the dataset consists of images related to various monuments, each belonging to a specific class representing a unique heritage site. These classes include famous landmarks such as the Taj Mahal, the Gateway of India, and the Qutub Minar. Importing the dataset involves organizing these images into appropriate directories or data structures, facilitating their use in model training and evaluation. The third step is data pre-processing. So image data generators are employed to pre-process the dataset before training the deep learning models in this step. So this step involves tasks such as rescaling, resizing, and augmenting the images to enhance model generalization and performance. So, data augmentation techniques help diversify the dataset by applying transformations such as rotation, flipping, and zooming, thereby enriching the model's ability to learn from varied inputs. The next step is training and building the models. So, the next step involves training multiple deep learning models using the imported dataset. Architectures like VGG16, MobileNet, ResNet, and others are constructed and trained on the dataset to learn the features relevant for classifying monuments. During training, the models iteratively adjust their parameters to minimize the prediction error, optimizing their ability to distinguish between different heritage sites based on input images. The next step is performance comparison. So, after training, the performance of each model is evaluated using metrics such as accuracy, precision, recall, and F1 score. These metrics provide insights into the model's effectiveness in correctly classifying monuments and avoiding misclassifications. So, by comparing the performance across different models, we can identify the most suitable architecture for the task of monument classification. And in the next step, we develop a user interface using Flask, a web framework for Python, integrated with SQLite for user sign up and sign in functionalities. The front end allows users to interact with the trained model by uploading images of monuments. Through a user friendly interface, users can receive classification results indicating the name of the recognized monument. So, after signing in, users input images of monuments through the front end interface, and the trained model processes these images to classify the corresponding monument name. The model's prediction is then displayed to the user, providing a seamless and intuitive experience for monument recognition. Now we'll understand about the algorithms used. So, the first algorithm built is VGG16, that is Visual Geometry Group 16. So VGG16 renowned convolutional neural network architecture comprises 16 layers including convolutional and max pooling layers. Its simplicity and ability to capture intricate features in images make it ideal for this project. VGT16 excels in recognizing patterns and details, aligning well with the varied characteristics of heritage monuments images for accurate classification. The next algorithm built is MobileNet. So, MobileNet is a lightweight convolutional neural network architecture optimized for mobile and embedded devices. It utilizes depth-wise separable convolutions to reduce computational complexity while maintaining performance. Its efficiency makes it suitable for this project, enabling fast and accurate detection of heritage monuments on resource constrained platforms. The next one is MobileNet V2. So, MobileNet V2 is an enhanced version of the MobileNet architecture designed to further improve efficiency and performance. It introduces inverted residual blocks with linear bottlenecks and shortcut connections, facilitating faster convergence and better accuracy. MobileNet V2's lightweight design and superior performance make it ideal for this project, enabling efficient detection of heritage monuments with minimal computational resources. The next algorithm built is ResNet 50. So, ResNet 50 is a deep convolutional neural network architecture characterized by its residual blocks, which allow for the training of very deep networks without encountering the vanishing gradient problem. Its design incorporates skip connections that bypass one or more layers, facilitating the flow of gradients during training. ResNet 50's depth and skip connections make it suitable for this project, enabling the effective extraction of intricate features from heritage monument images, thereby improving classification accuracy. The next algorithm built is Inception V3. So, Inception V3 is a convolutional neural network architecture known for its deep and complex structure, featuring multiple parallel convolutional pathways, including inception modules. These models perform convolution operations of varying kernel sizes, enabling the network to capture both local and global features effectively. Inception V3's sophisticated architecture makes it suitable for this project as it facilitates the extraction of diverse and intricate features from heritage monument images, enhancing classification accuracy. The next one is Exception. Exception is a convolutional neural network architecture that extends upon the inception architecture by replacing standard convolutional layers with depth-wise separable convolutions. These convolutions separate spatial and channel-wise operations, leading to a more efficient use of parameters and improved feature representation. Exceptions enhanced efficiency and performance make it well suited for this project, enabling accurate detection of heritage monuments while minimizing computational resources. The next algorithm built is DenseNet 169. It is a CNN architecture featuring dense connectivity between layers, allowing each layer to receive inputs from all preceding layers within a dense block. This facilitates feature reuse and propagation, enhancing feature representation for accurate detection of heritage monuments by capturing intricate patterns and details in images. The next one is ResNet 101. It is a CNN architecture again characterized by its deep structure comprising 101 layers. It introduces residual connections which enable the training of very deep networks by mitigating the vanishing gradient problem. ResNet 101's depth and skip connections facilitate effective feature extraction from heritage monument images, enhancing classification accuracy in this project. The next one is LeanNet. So LeanNet consists of several layers including convolutional, pooling, and fully connected layers. It utilizes convolutional filters to extract spatial features and pooling layers to reduce dimensionality. Although it is an early CNN model, LeanNet's simplicity and effectiveness in image classification tasks make it a suitable choice for this project, especially for detecting heritage monuments where the images may not be highly complex. The next algorithm built is EfficientNet V2S. It is a variant of the EfficientNet architecture that emphasizes both efficiency and performance. It achieves this by employing a combination of depth-wise separable convolutions, efficient inverted residuals, and squeeze and excitation blocks. This design allows for better parameter efficiency and scaling, making EfficientNet V2S ideal for this project where resource efficient yet accurate monument detection is crucial, especially for deploying on devices with limited computational capabilities. And the last algorithm built is CNN, that is convolutional neural network. So CNNs are deep learning architectures adept at processing grid-like data like images. They utilize convolutional filters to extract features and pooling layers to reduce dimensionality. Efficient at learning intricate patterns, CNNs excel in image classification tasks, including heritage monument detection, making them well suited for this project's recognition needs. Now we'll see the comparison graphs. So this is the bar graph comparing accuracy scores of different algorithms. In this graph on x-axis, I have algorithm names and on y-axis I have accuracy scores. So accuracy measures the overall correctness of predictions, showing the percentage of correctly classified instances. This is recall scores comparison graph. In this graph on x-axis, I have algorithm names and on y-axis I have recall scores. Recall measures the ability to identify all relevant instances, showing how many actual positives were correctly predicted. This is precision scores comparison graph. In this graph on x-axis I have algorithm names and on y-axis I have precision scores. Precision measures the accuracy of positive predictions, indicating how many predicted positives were actually correct. And this is F1 scores comparison graph. In this graph on x-axis, I have algorithm names and on y-axis, I have F1 scores. F1 score combines precision and recall into a single metric, balancing accuracy and completeness in predictions. So the algorithm which is best performing in all the performance metrics will be used for classifications. And we can see MobileNet V2 has outperformed all other models in all the performance metrics. So we will deploy it in Flask. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So this is dataset folder in which I have required monument images on which we will train the models. This is models folder in which I have model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. This is sample folder in which I have monument images on which we'll make the classifications. This is static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. This is Notebook Jupyter source file, which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. So now copy the path of the code folder from the address bar of the file Explorer. I'm copying it. Open Anaconda prompt. So now use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost, and port unless configured differently. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a sign up link, click on it. So if you are new users, we have to register first, fill in all these details and click on register button to sign up. And if we already have account, we can directly log in by clicking on the sign in link. So as I'm already a member, I'm clicking on the sign in link. Here we have to give our credentials, username and password and click on submit button. So it has redirected us to the classifications page, and here we have to upload any monument image and the application will recognize the monument from the image. Click on choose file button. So from sample images folder, I'm selecting this image and click on open. The image is loaded. Now click on upload button. So we can see the application has recognized the monument as Charminar. We'll try again. Click on back link. Click on choose file button. So this time I'm uploading this image and click on open. The image is loaded. Now click on upload button. So we can see the application has correctly recognized the monument as Humayun's tomb. Now we'll try giving another image. Click on choose file button. So this time I'm uploading this image and click on open. The image is loaded. Now click on upload button. So here we can see the recognition that is Golden Temple. So it has correctly classified it as Golden Temple. Click on back. We'll try again. Click on choose file button. This time I'm uploading this image and click on open. The image is loaded. Now click on upload button. So here we can see it has correctly recognized it as Gateway of India. Now we'll try uploading any image from Google. So we'll download any image from the Google. I'm downloading Taj Mahal image. So I'm downloading this image. Now we'll upload the downloaded image. Click on choose file button. Select the downloaded image. Click on open. The image is loaded. Now click on upload button. So here we can see it has correctly classified it as Taj Mahal. So similarly, we can upload any monument image and can get the classification. Now click on logout. So the conclusion here is the project has achieved its goal of implementing deep learning algorithms for heritage monument detection, including VGG16, MobileNet, ResNet 50, and others, demonstrating the feasibility of leveraging advanced technologies for cultural heritage preservation. By automating the detection and monitoring of heritage monuments, the project contributes significantly to their preservation and protection, ensuring that these invaluable cultural treasures are safeguarded for future generations. Among the various deep learning architectures evaluated, MobileNet V2 emerged as the top performer, showcasing superior accuracy, precision, recall, and F1 score in monument classification tasks, validating its efficacy for heritage preservation initiatives. And the integration of Flask with SQLite for user sign up and sign in functionalities provides a robust framework for testing the trained models in real world scenarios, offering users a seamless and intuitive interface for monument recognition. So, governments, heritage conservation organizations, historians, researchers, and local communities are the primary beneficiaries of this project, benefiting from enhanced methods for heritage monument detection and preservation. Future iterations could explore additional enhancements such as real time monitoring, multimodal data fusion, and scalability to further advance heritage preservation efforts globally.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.